Since this unit of chemical bonding also includes the diversity of matter, we are going to look a little bit away from molecular compounds and look a little bit more at ionic compounds and metallic compounds. Now, it's not saying that we won't look at all at molecular compounds with covalent bonds in this little lesson, but we will take another look at some of our other compounds. So, we're going to take a look at the structure and physical properties of solids. So, some properties of solids. All solids, including elements and compounds, have a definite shape and volume. Okay, they're virtually incompressible and don't flow readily. So, we have incompressible, meaning that when you apply a pressure to them, they generally either do not compress or they will shatter or fracture, which is pretty interesting. And some of them have a definite shape, but they are a little bit malleable or ductile depending on the metal that we're looking at, or a solid that we're looking at. So some properties of solids, these are some physical properties. It would be hardness, melting point, okay, conductivity, malleability, also boiling point is another one that you can consider. Okay, the structure and properties are related to the forces between our particles. So we talked a little bit about intermolecular forces, but we're also going to look at properties that are not just in molecular compounds. So it's between our particles, whether that be between some atoms or between molecules, but it's all to do with those forces between our particles. Now, first off, we can look at ionic crystals. Now, ionic crystals are crystals formed from ionic compounds. Now, essentially, when we form an ionic compound, we have combinations of alternating ions. Now, if we look at our sort of diagram on the left here, you'll see that we have alternations between sodium and chloride, and we have sodium and chloride ions. Now, this would be a salt crystal. And in order to form a salt crystal, we had to have alternating cations and anions in this structure. Now, the reason why they order themselves this way is partially because of the ionic bonds as well as electrostatic repulsion. So we like to have a negative bonded to a positive in every direction, creating this crystalline structure. Now, the formation of ionic crystals can either be through binary ionic compounds, which would be like the formation of sodium plus chlorine gas, giving us sodium chloride. Or we can have compound formation of ionic crystals, which would be like the formation of or the combination of ammonia plus my hydrochloric acid forming ammonium chloride. So we see a compound plus a compound gives us an ionic crystal. And again, it is all due to our ionic bonds that are formed between our cation and our anion. So, in this case, we have our sodium cation, our chloride anion forming sodium chloride, and I guess I should balance this to make it a proper chemical reaction here. So I'd have 2 sodiums and 2 sodium chlorides. And in this case here, this would be balanced as a chemical reaction below. And again, it doesn't matter how these ionic crystals are formed. It matters based on the anion and cation that is formed in our compound. So, the state of matter for all ionic compounds is a solid. And whatever pattern of the crystal lattice, however that is organized, and that will be dependent on the anion and cation, there's the maximum number of oppositely charged ions close by. So like charges will repel and opposite charges will attract. So we can create a crystal lattice by having, if this is a negatively charged particle, surrounding it as tightly packed as we can. And this is, again, dependent on the structure of our ionic compound, whether I have 2 cations for every 1 anion, that will be dependent. But essentially, I'm going to have an organization of these ions that is going to create as tightly knit, as close as we can, with our like charges. So if this is a positive, this is a positive, this is a positive, these are negatives. Okay, we're going to create a really tightly knit compound, and essentially that will form a nice crystal lattice, or sort of a structure that keeps all of these things bonded together. Okay, so again, our like charges repel, our opposite charges attract, and we get the construction of a crystal lattice, or a structure. Now, a crystal lattice is essentially just that arrangement of ions in an ionic compound. It's that structure. It forms strong attractions. This is because we have like charges repelling and opposite charges attracting. They're often very brittle, and they're surrounded by their opposite charge, which we've talked about in our previous slide there. Now, we can also have things like metallic crystals. So in a metallic crystal, they're very metallic crystals are a little bit on the rare side, but they're very shiny, silvery, flexible solids that are metals. Okay, and they're solid, most of them, maybe except for mercury, and they're good electrical conductors as well as thermal conductors. Okay, and they range from sort of a hard to a soft malleability, and a high melting point to a low melting point. So they generally have very, very closely packed structures, and we show that they can have a very crystalline structure. Now, essentially, if you remember, based on our metallic bonding, we have a bunch of positively charged nuclei that are surrounded by electrons like this, that act as the glue that holds these structures together. Now, again, some metallic properties that we have. The first one is shiny and silvery. Now, the reason why metallic substances are shiny and silvery is because our valence electrons will absorb and re-emit energy from all wavelengths of visible light. So valence electrons absorb and re-emit energy from all wavelengths. Oops. All right, so that's interesting, and that's all to do with our valence electrons. Now, flexible means that there's non-directional bonds. Now, we know that because there's just these glue. There's just ions that hold electrons that hold our nuclei together. So they're flexible. They're non-directional bonds, which means that we can have these sort of glue, or the bonds that slide over top of each other, okay, and they can still remain close knit. So non-directional bonds. Okay, they're also electrical, they have electrical conductivity. Okay, and this is because valence electrons can freely move through they can freely move between those nuclei, meaning that they are electrically conductive because conductivity is dependent on the movement of electrons. Crystalline because they have that electrostatic glue. Okay, so they have those electrons or electrostatic glue that hold them in that particular tightly packed shape. So they are held together by that electrical or electrostatic glue. So all of these metallic properties that we have are based on these electrons and being able to either move or surrounding the nuclei, but essentially all of the properties that metals have are due to our electrons. So we can also look at molecular crystals. Now, molecular crystals, a prime example, is something like sugar or dry ice, which is solid carbon dioxide. So we have elements or compounds. Again, we can have solid elements as iodine, that is a molecular crystal, or ice. So we have water that has been frozen. They have relatively low melting points, okay, and are non-conductors. We have London dispersion, dipole-dipole, and hydrogen bonding forces that are present, but they're less strong than our ionic or covalent bonds. So we have these extra intermolecular forces that are contributing to their boiling point and melting points potentially. They're less strong than those covalent bonds that hold them together, but it does contribute to some of their physical properties. Now we also have covalent network crystals. Now covalent meaning covalent bonds, and we have a network. We have many of these covalent bonds and they form a crystal. Now they're generally hard and brittle and they have quite a high melting point. And a covalent network is a 3D arrangement of those continuously linked covalent bonds. And in this situation, our electrons are not free to move. They remain in their position. A prime example of a covalent network is a diamond. So we see that there's a lot of uses of these covalent networks to make things very strong because they are very brittle and they have a high melting point, as well as they are don't have any electrons that are free to move. We see that carbon is a prime example of a covalent network because it forms many different covalent networks. The first we can talk about is diamond, and I'll show you a structure of what the diamond looks like based on our carbon-to-carbon covalent bonds. We also have graphite, which is in your pencil lead. Okay, graphite is also another carbon substance. We have buckyballs, which are very magnetic type balls that are used for different games, things like that. And we have carbon nanotubes as well, which is a different arrangement of our carbon-to-carbon covalent bonds. Here's our examples. Our diamond, you'll notice, is very, very structurally sound. We know that triangles are sort of our strongest shape that we have, and you'll notice that there's several sort of triangular shapes amidst this carbon-to-carbon covalent bond, but you'll notice it's very, very structured, very, very organized when we create that. That is why this is one of the hardest or the hardest substance that we have. Okay, graphite is organized very different. It has, again, a six-sided shape here, but they form in planes. Now we have, in this example, we have 3 different planes of this graphite, and the reason why you can write with your pencil is these graphite planes slide on top of each other, and they essentially, what happens is a layer gets slid off and onto your paper, and the reason why we get that is because they are mobile sort of sheets that can slide on top of each other. This example here is a buckyball. How do I spell buckyball? Now, of course, that I've written that down, I don't, there we go. There we go. So this is a buckyball. You'll notice it has a different arrangement of its carbon atoms. And then we have this carbon nanotube, which can be used for a variety of different functions as well. So depending on how these carbon-to-carbon covalent bonds arrange themselves in a different network, we can get very different properties from our covalent network. Another interesting sort of property of a metal / a non-metal is a semiconductor. Now, More commonly, we talk about semiconductors of being a silicone-based product. Now, it's a silicon-based product that's been doped with elements from either group 13 or 15. And we think these elements with the valence orbitals are full, but the electrons cannot move. So what happens is we have these high energy level elements that have been combined with our silicon, and this is involving a great deal of research, but essentially these silicon semiconductors is what is the primary component in your microchips in any sort of computer devices. So we have the highest energy levels may be thought of being full of electrons that are unable to move from atom to atom, and normally this would make a substance a non-conductor. But in a semiconductor, electrons require only a small amount of energy to jump. So we only require, now these electrons can't move, however, when we apply energy, they can jump small distances. Oops. So this is what makes them semiconductors. Until we apply an energy, they do not jump energy levels. Okay, so once they jump to a higher energy level, they can move to another atom more easily, which is pretty interesting. All right, so a summary of what we've talked about in this lesson is that ionic crystals are formed from cations and anions. Now, the force between them are ionic bonds. Now, the properties of ionic crystals are that they're hard, brittle, they're medium to high melting point, and they're liquid and solution conductors. So if you were to melt them into a molten, okay, which is very important, if you were molten ionic compounds, they are conductive, as well as they are conductive when they're dissolved in water. We have metallic crystals, which are formed from cations and electrons. Okay, so these are just our metals. The force is a metallic bond. They're soft to very hard, depending on the metal that we're talking about. They're solid and liquid conductors. So again, if it's a solid metal, it's a solid conductor. If it's a liquid metal like mercury, it's a liquid conductor. And they're ductile, malleable, and lustrous. Now, malleable again means that they bend easily, and ductile means that they form, they can be pulled into a single wire quite easily. And they're lustrous, meaning they're shiny and brilliant looking. We have molecular crystals. Again, the entities are molecules. We have any sort of intermolecular force that are holding them together. They're generally soft. They generally have a low melting point. They're non-conducting solids. They don't have any movement of electrons, which we know. And there can be liquid or in solution. So they're non-conducting solids, liquids, or solutions. Okay, now we see that we also have a covalent network. We have atoms in a covalent network, like our carbon example. We have a covalent bond keeping those things together. They're very, very hard. They have very high melting points, and they're non-conducting as well. So pretty interesting as we go through the summary to see the main forces of these crystalline structures. And as well, we talked about our semiconductors and how we can dope a silicon particle with an element from group 13 or 15 to make it so that if a small amount of energy is applied, we can have those electrons jumping, which is how we create many of our electronic devices that we use on a daily basis. So this is wrapping up the end of our chemical bonding unit. If you need to go back and review any note package at this point, I really suggest doing that before you go on to your unit exam. So, good luck.